Hey, what's up? It's Red Wasp. Welcome to the channel. Welcome to the first video of the channel, in which I'm going to do a walkthrough of the race conditions lab from TryHackMe, where we're going to learn about race conditions and how and why they affect web applications from a web application security perspective. So this video is for educational purposes only, and we are practicing what we learn in a controlled environment. These are the 7 tasks that we have. We have 1 exercise, 1 challenge. So let's get right into it. Task 1 is introduction. Let's say we are tasked with testing the security of an online web application. Many questions pop up. Can we reuse a single $10 gift card to pay for a $100 item? Can we apply the same discount to our shopping cart multiple times? The answer is maybe. If the system is I can't say this word. If the system is susceptible to a race condition vulnerability, we can do all this and more. This room introduces the race conditions vulnerability. So what is a race condition? A race condition is a situation in the computer programs where the timing of events influences the behavior and outcome of the program, right? It typically happens when a variable gets accessed and modified by multiple threads. This is very key. Due to a lack of proper lock mechanisms and synchronization between the different threads, an attacker might abuse the system and apply a discount multiple times or make money transactions beyond their balance. So the learning objectives are race conditions vulnerability and using Burp Suite repeater to exploit race conditions. We'll discover more about the repeater module in Burp Suite. Along the way, you'll also learn about threads and multi-threading, state diagrams. The learning prerequisites to follow this room, we recommend familiarity with HTTP protocol, web applications, and Burp Suite. These are the rooms and modules that we should have had done first before getting here. I think it pays well. Let the race begin. I'll open task 2. In this task, we'll provide a quick overview of the following terms: program, process, thread, and multi-threading. So these are kind of like the building blocks of what we'll get into later, race conditions themselves, and etc. So program is a set of instructions to achieve a specific task. You need to execute the program to accomplish what you want. Unless you execute it, it won't do anything and remains a set of static instructions. Think of it as a recipe. You just downloaded a new coffee recipe that includes a variety of herbs such as cardamom and cinnamon. These are the instructions. 1, 2, 3, 4, these are a set of instructions. So unless someone carries out the above instructions, no coffee will be served. Compare this to our minimal Flask Python hello world server. The code below dictates that the app will listen on port 8080 and respond with a minimal greeting HTML page that contains hello world. However, we must run these instructions, this program, right? Instructions, program, same thing. Program instructions before we expect to get any greeting pages. So this code is for demonstrative purposes only. We have this is a real world example of this code, or maybe this is a real world example of these instructions. But they're both programs, they're both instructions, right? Import the Flask class from the Flask module, create an instance of the Flask class representing the application, define a route for the root URL. So these are all just instructions. And then this checks if the script is being run directly as the main program and not being imported as a module. So we have this check, and then we have the running of the Flask application, right? And more information: the host 0.0.0.0 allows the server to be accessible from any IP address. The port 8080 specifies the port number on which the server will listen. So if we go to processes, one afternoon you decide to try out this new coffee recipe you downloaded online. You start going through the recipe one step at a time. You are in the process of making this coffee recipe. While in the process of executing the instructions, you might get interrupted by an urgent call, or you might work on another job while waiting for the water to heat. Interruptions and waiting are generally unavoidable. The act of carrying out the recipe instructions to make coffee is similar to the process of executing program instructions. So a process is a program in execution. In some literature, you might come across the term job. Both terms refer to the same thing, although the term process has superseded the term job. Unlike a program, which is static, a process is a dynamic entity. It holds several key aspects, in particular, a program, memory, a state. A program is the set of instructions, the executable code related to the process. Memory is a temporary data storage that the program or the process uses while it's in execution, right? And state is a process usually hops between different states. After it is in the new state, i.e. just created, it moves to the ready state, ready to run, or i.e. ready to run once given CPU time. So this is the diagram of what's being explained here. Once the CPU allocates time for it, okay, let's start this paragraph again. A process usually hops between different states. After it is in the new state, this one I just created, it moves to the ready state. It's admitted to the ready state, ready to run given CPU time. So it's ready to run after the CPU allocates time for it, which is in this section right here, right? After it allocates time for it, it goes to the running state. Furthermore, it can be in the waiting state pending input or output or event completion, right? So it goes from the running state to the waiting state, waiting for like input, output, or an event. So it kind of like loops, right? Loops over here, and unless if we don't exit it, it's not terminated, right? So it needs to be terminated. So we need to interrupt it. We need to exit it some way, shape, or form. So if you run the Flask code above, a process will be created and it will listen for incoming connections at port 8080. In other words, it will spend most of its time in the waiting state, this one here. And when it receives an HTTP GET request, it will switch to the ready state, this one, waiting for its turn to run based on the CPU scheduling, this section here. Once in the running state, it sends the HTML page back to the client and returns to the waiting state. So again, yeah, it goes in this loop. No? From the server's perspective, the app is servicing clients sequentially, i.e. client requests are processed one at a time. Note that the Flask is multi-threaded by default since version 1.0. We use the arguments hyphen without hyphen threads to force it to run single-threaded. demonstrative purposes only, Flask run -- without -threads -- host equals 0.0.0.0. So I think we have like an understanding of what's going on here and here as well. Threads, let's wrap up with another coffee analogy. Consider the case of a commercial espresso machine in a coffee shop. Let's say it has two ported filters, right? At the start of the work day, the barista turns on the espresso machine, and whenever a customer orders an espresso, one ported filter is used to prepare an espresso shot for them. Does another customer order an espresso? No problem, the second ported filter to the rescue. The warmed up espresso machine is the process. So this is the espresso machine, which is the process that has a set of instructions, memory, and what else? States. Program memory states. Each new order is assigned a new porter filter. That's the analogy for the thread. Okay, so a thread is a lightweight unit of execution. It shares various memory parts and instructions with the process. In many cases, we need to replicate the same process repeatedly. Think of web servers serving thousands of users the same page or a personalized page. We can adopt one of two main approaches. Serial, one process is running. It serves one user after the other sequentially. New users are on queued. So we're talking about, we're talking about one user at a time, right? Sequentially. Parallel, we're talking about one process is running. It creates a thread to serve every new user. New users are only on queued after a maximum number of running threads is reached. So here it's it's kind of like a multi-thread situation at the same time until a maximum number of running threads is reached. And then users are on queued, right? The previous app can run with 4 threads using Unicorn. Unicorn, also called the Green Unicorn, is a Python WSGI HTTP server. WSGI stands for Web Server Gateway Interface, which bridges web servers and Python web applications, right? In particular, Unicorn can spawn multiple worker processes to handle incoming requests simultaneously. By running Unicorn with the workers for option, we are specifying that we want 4 workers ready to tackle clients' requests. Moreover, the threads to option indicates that each worker process can spawn 2 threads, right? So this is the running of Unicorn with the option workers 4, threads 2. I wonder what B means. B definitely means something. So it is worth noting the following. It is impossible to run more than one copy of this process as it binds itself to TCP port 8080. A TCP or UDP port can only be tied to one process. Process can be configured with any number of threads, and the HTTP requests arriving at port 8080 will be sent to the different threads. So you download an instruction booklet on how to make an origami crane, right? What would the instruction booklet resemble in computer terms? I'm guessing a program, since it's a set of instructions. What is the name of the state where a process is waiting for input or output events? For an input or output event, waiting states, right? If you go back to the diagram, this is the states. The process is waiting. Okay, Task 3, real world analogy. Picture the following situation. You call a restaurant to reserve a table for a crucial business launch. You're familiar with the restaurant and its setup. One particular table, number 17, is your preferred choice, considering it has a nice view and it is relatively isolated. You call to make a reservation for table 17. The host confirms it is free as no reserve tag is placed on it. At the same time, another customer is talking with another host and making a reservation for the same table. Who really reserved the table? That's a race condition. So why did this happen? This unlucky situation happened because more than one host was taking reservations. Furthermore, so why did this happen? This unlucky situation happened because more than one host was taking reservations. Furthermore, it took the host a few minutes to fetch the reserve tag and put it on the table after updating the daily reservation book, right? There's at least a 1 minute window for another client to reserve a reserved table. Similarly, when one thread checks a value to perform an action, another thread might change that value before the action takes place. So, yeah, a few things are key here. The 1 minute window in which two hosts, are looking at the same table, resource, and they want to reserve it, they want to access it at the same time. Again, it goes back to what was said in the introduction, lack of proper lock mechanisms and syncs between the different threads. So we're gonna see more of that, a bit more of that later. So, example A. Let's consider this scenario. A bank account has $100. Two threads try to withdraw money. At the same time, thread 1 checks the balance, sees $100, and withdraws $45. Before thread 1 updates the balance, thread 2 also checks the balance, incorrectly sees $100, and withdraws $35, right? We cannot be certain which thread will get to update the remaining balance first. However, let's assume that it is thread 1. Thread 1 will set the remaining balance to $55. Afterwards, thread 2 might set the remaining balance to $65 if not appropriately handled. Thread 2 calculated that $65 should remain in the account after the withdrawal because the balance was $100 when thread 2 checked. In other words, the user made 2 withdrawals, but the account balance was deducted only for the second one because thread 2 said so. Interesting. Example B. Let's consider another scenario. A bank account has $75. Two threads try to withdraw money at the same time. Thread 1 checks the balance, sees $75, and withdraws $50. Before thread 1 updates the balance, thread 2 checks the balance, incorrectly sees $75, and withdraws $50. Thread 2 will process with the withdrawal, although such a transaction should have been declined. Examples A and B demonstrate a time of check to time of use vulnerability, right? So, example code. Consider the following Python code with 2 threads simulating a task completion by 10% increments. So, this code, I think, produces this result, right? We have a set of instructions again, import threading, shared variable. We have the function of the 10% increments, right? We create 2 threads. We start the threads, and then we wait for both threads to finish. And then at the end, we print both threads have finished completely. So these two threads start together, they do nothing except print a value on the screen. Consequently, one would expect them to finish simultaneously, or at least the results to be consistent. However, in the program above, there is no guarantee which thread will finish first and how early it will be. Below is the first execution output. So we execute it on the terminal. This is the first execution. This is the second execution. Obviously, they're very different. I'm not sure, but they're different. They're not the same, right? So running this program multiple times will lead to different results. In the first attempt, thread 2 reached 100 first. However, in the second attempt, thread 2 reached 100 second. We have no control over the output. If the security of our application relies on one thread finishing before the other, then we need to set mechanisms in place and ensure proper protection, like locks and syncs, right? Consider the following two examples to better understand the bug's gravity when we leave things to chance. On the attack box, you can save the above Python code, run it multiple times to observe the outcome. For instance, save it as race.py. You can run the scripts using the Python race.py command. Causes. As we saw in the last program, two threads were changing the same variable. So two threads accessing the same resource or variable. Whenever the thread was given CPU time, it rushed to increase X by 1, right? Consequently, these two threads were racing to increment the same variable. This program shows a straightforward example happening on a single host. Generally speaking, a common cause of race conditions lies in shared resources. For example, when multiple threads concurrently access and modify the same shared data. Examples of shared data are a database record and an in-memory data structure. There are many subtle cases, but we'll mention three common ones. Parallel execution. Web servers may execute multiple requests in parallel to handle concurrent user interactions. These requests access and modify shared resources or application states without proper synchronization. It can lead to race conditions and unexpected behavior, right? Database operations. Concurrent database operations such as read, modify, write sequences can introduce race conditions. For example, two users are attempting to update the same record simultaneously may result in inconsistent data or conflicts. The solution lies in enforcing proper locking mechanisms and transaction isolation. Third-party libraries and services. Web applications often integrate with third-party libraries, APIs, and other services. So if these external components are not designed to handle concurrent access properly, race conditions may occur when multiple requests or operations interact with them simultaneously. So does the presented Python script guarantee which thread will reach 100% first? No. Nay. In the second execution of the Python script, what is the name of the thread that reached 100 first? Second execution. First execution. I'll go with thread 1. Thread 1 reached 100 first. Thread 1. Okay, great. Great. Task 4, web application architecture. Let's visit web application architecture to explain how race conditions are possible. So, the client-server model. Web applications follow a client-server model. The client is the program or application that initiates the request for a service, right? For example, when we browse a web page, our web browser requests the web page file, the file from a web server. The server is a program or system that provides these services in response to incoming requests. For instance, the web server responds to an incoming HTTP GET request and sends an HTML page or file to the requesting web browser client. So client server request response. Generally speaking, the client server model runs over a network. The client sends its requests over the network, and the server receives it and processes it before sending back the required resource. So a typical web application has multiple tiers, or 3 tiers. We have the presentation tier, the application tier, and the data tier. The presentation tier, this tier consists of the web browser on the client side. Application tier, this tier contains the web application's business logic and functionality. So we have server-side programming languages like Node.js, and PHP. The data tier is responsible for storing and manipulating the application data. So we have database management systems like MySQL and PostgreSQL. Typical database operations: creating, updating, deleting, and searching existing records. You have a diagram here: web browser, internet, web server, web application. So I think the request comes from here and the response comes from here. The states, let's visit some examples from business logic before diving deeper. We'll consider the following examples: validating and conducting money transfer, validating coupon codes and applying discounts. So we have the validating and conducting money transfer. Consider the example of transferring money to a friend or your other accounts. The program will progress as follows. User clicks confirm transfer. Application queries the database. Database responds to the query. This kind of lines up with these states over here. User clicks confirm transfer, that's on the browser, which is on the presentation tier, or browser on the client side. Application queries a database, probably using Node.js and PHP in the application tier. And then database responds to the query. So the application data and resources or variables or records, that's accessed in the data tier. So then the response goes back to the source, to the web browser. It's on the client side. So now we have a fork. Amount within limits, like an if condition. If not, display error message. If yes, conduct transaction. In an ideal scenario, the code above leads to 2 program states: amount not sent and amount sent. Amount not sent, amount sent. If the amount is within limits, it goes from an amount not sent to amount sent. If not, kind of loops back because it exceeds the limits. Validating coupon codes and applying discounts. Let's consider the example of applying a discount coupon. The user goes to their shopping cart and adds a coupon to get a discount, right? The steps might be something along the following lines. User clicks apply coupon. Application queries the database. Database responds to the query. If condition, right here, is the coupon valid? Is if yes, apply discount. If not, display error message. The above code leads to a few program states: coupon not applied, coupon applied, coupon not applied. If the coupon is valid, coupon applied. If not, circles back to coupon not applied. So 2 states. Think again. Let's continue our analysis of applying a discount code. Ideally, we expect 2 states: coupon not applied and coupon applied. However, this is too simplistic to depict real sophisticated scenarios, right? We can add an intermediary state checking coupon applicability. So coupon not applied. Add coupon. Check coupon applicability. Is coupon applicable? Coupon apply. If not, it circles back to the first state. Depending on how the application is developed, we can expect more states. For example, checking coupon applicability might involve two states: checking coupon validity and checking coupon constraints. A coupon might be valid, but existing constraints prevent it from being applied, right? Similarly, coupon applied might be divided into two states, one of which is recalculating total. So coupon not applied, to you add coupon, check validity, coupons valid, check constraints, coupon applicable, recalculating total, mark coupon as applied, coupon applied. And if anything is, I don't know, something's not, if the coupon is not valid, circles back. If it's not applicable, circles back, and so on. So why is this important for race conditions? In the state diagram above, we can see that we pass through multiple states before the coupon is marked as applied. Let's draw the states on a time axis as shown below. Coupon not applied. Check validity. Check constraints. Recalculating total. Coupon applied. So we have add coupon here. We have mark coupon is applied on time axis. So there's a time window between the instant we try to add a coupon and the instant where the coupon is marked as applied and cannot be applied again. As long as the coupon is not marked as applied, most likely no controls prevent it from being accepted repeatedly. We might be able to apply it multiple times during this time window, right? So this situation is similar when considering the states for the program making a money transfer, right? Although ideally speaking, it would be two states considering the business logic, we can easily update the diagram to include three states. The reason is that we expect some time spent checking the account balance and limits. Although this amount of time might be brief, it's not zero. If we dig deeper, we can uncover more hidden states. Amount not sent and amount sent here, but then we confirm transfer and we check balance and account limits. Okay, balance is all good. Account limits all good. Account amounts within limits, amount sent. If not, circles back to the first state. However, if the application is vulnerable, we still have one challenge to overcome, which is timing. Even in vulnerable applications, this window of opportunity is relatively short. Therefore, exploiting it necessitates that our requests reach the server simultaneously. In practice, we aim to get our repeated requests to reach the server only milliseconds apart. How can we get our duplicated requests to reach the server within this short window? We need a tool such as Burp Street. So how many states did the original state diagram of validating and conducting money transfer have? 2, I'm guessing. 1, 2, 1, 2. So 2. How many states did the updated state diagram of validating and conducting money transfer have? Same diagram, but I'm guessing 3 states. This is the updated one. Money transfer. 3. How many states did the final state diagram of validating coupon codes and applied discounts have? This is the final one, right? 1, 2, 3, 4, 5. Awesome. That was task 4. So now we're getting a little practical, exploiting race conditions. Click on the Start Machine button on the right to start the attached VM. Click on the Start Attack Box button at the top to start the attack box. On the attack box, browse to HTTP machine IP. So let's start this machine. I'm going to be using my own VM that I connected via VPN through the VPN settings and the configuration file, which should be very simple. So we wait for the machine to start. So we have the machine here, and I'm just gonna pass this over to my VM just to decrease transport between tabs. So we have the IP address here. We just need to copy this, load it into a tab. Okay, let me start my Burp Suite. This is the Burp Suite Community Edition. We started. We already have Foxy Proxy here enabled for Burp. So we refresh it. Okay, we have a login form. These are the credentials for 2 users. User 1, this number, password, pass1234. User 2 has the same password but different number. So this web application belongs to a mobile operator and allows phone credit transfer. In this demo, we'll check if the system is susceptible to a race condition vulnerability and try to exploit it by transferring more credit than we have in our accounts. All right. So first, we need to explore and study how the target web application receives HTTP requests and how it responds to them. Using Burp Suite Proxy, click Open Browser under the Intercept tab. To get an error message about enabling browser sandbox, you must manually change the settings. In this case, click Settings on the top right of your Burp Suite window. Click the Burp's browser and under Tools, and check Allow Burp's browser to run without sandbox. I'm using Firefox. It's already routed via Foxy Proxy. Using the bundled browser, we can browse the target site and study how it processes HTTP requests, notably the post HTTP request and the related response HTTP history. Tab logs every HTTP request and respective response. So we can log in to either of accounts. Click the Pay Recharge button. Let's make a credit transfer. Click the Transfer button and enter the mobile number of the other account along with the amount you want to transfer. You can try to transfer an amount that exceeds your current balance and a small amount such as $1 to see how the system responds in each case. So I usually minimize my browser like so, and just so I have the browser and Burp Suite side by side. We go to Proxy, HTTP history. I'm already recording, getting through some requests. I don't have Intercept on, but yeah, so let's log in. Let's take in this. Pass 1, 2, 3, 4. So we have a current balance of 6.52. Pay and recharge. We take in this. Let's try an amount of 1, right? let's check in this URL, just see if it lines up. Transaction successful. We have like some TryHackMe requests here, but let's search for that URL. Transaction successful. I think this is the one, right? Yeah, I think this is the one. This is the one. Let's check if this is the one. User ID. I think we're searching for a post. We're searching for a post request. I think this is the one. Yeah, exactly. So this is the one. If we maximize burp, we'll see that we had a target phone number. This is the phone number. We confirm the phone number and then the amount, which is 1. So we send this to the repeater. We can quickly press Control, hold Control, and press R, Control R, and you will see the repeater highlighted here. We send this to the repeater. This is the inspector. You can close it for now. We send this request. Wait for a response. So it gives a 204 no content. Dashboard transaction successful. Okay. Let's maximize this. If we go back, we have a current balance of 5.52. If we click on my line, last recharge. Okay. So that's the application. It's a phone credit transfer. So in the Burp Suite repeater, in the image below, we can see a post request. That's the post request we were looking for. The details show the target phone number and the transfer amount of 1.5. We transferred 1. And the response, we can infer the transaction is successful. So if we go back, amount of 1, right? Phone number, transaction successful. So then we have a screenshot of what we kind of just did. 1, 2, 3. Now that we have seen how the system reacts to valid and invalid requests, we haven't tried an invalid request. So let's try that. Same number. And then maybe now we could do like 50. We have insufficient balance, right? If we go back to the proxy and burp, just to search for that request, it's probably here somewhere. Yeah, it's right here. It's a post request and it says insufficient balance because we don't have sufficient balance, so it's an invalid value, right? I'm just gonna send this to repeater. Just keep it there, just so we can go back and see the requests and responses. If there's anything there, but okay, let's go back. Now that we've seen how the system reacts to valid and invalid requests, let's see if we can exploit a race condition. Right click on the post request you want to duplicate and choose send to repeater, because we want to duplicate the request so they can be sent simultaneously, right? So we sent the successful one to the repeater already. In the repeater tab, as shown in the numbered screenshots, click the plus icon next to the receive request tab and select create tab group. assign group name, and include the tab of the request. Okay, let me just do this just so we can do it step by step, right? So if we have, let's get rid of this tab for now. If we have this one, click the plus icon, new tab group, create tab group, new tab group, same thing. We'll just call this group 1 or transfer 1. Add a color. Okay, we'll keep it purple. Create, right? Oh, we need to add the tab to the group in order to create. Until then, the create button is gray. So we created, right click on the request tab and choose duplicate tab. If this option is not available in your version, you can press Ctrl R multiple times instead. Okay, so we right click, we say duplicate tab 20 times, duplicate. Next to the send button, the arrow pointed downwards will bring a menu to decide how you want to send duplicated requests. We have to create, duplicate, great. So next to the send button, this is what they mean. These options here of sending, of the request sending, right? Next, we will exploit the target application by sending the duplicated request. Using the built-in options in Burp Suite Repeater, the drop-down arrow offers the following choices. Send group in sequence, single connection. Send group in sequence, separate connection. Send group in parallel. So sending requests grouped in sequence. This is when we get into the types. Sending the group in sequence provides two options. Single connection, separate connections. Sending group in sequence over single connection. This option establishes a single connection to the server and sends all the requests in the group's tabs before closing the connection. This can be useful for testing potential client-side desync vulnerabilities, right? So then we have send group in sequence over separate connections. As the name suggests, this option establishes a TCP connection, sends a request from the group, and closes the TCP connection before repeating the process for the subsequent request. We tested this option to attack the web application. Sorry, the screenshot below shows 21 TCP connections for the different post requests in the groups that was sent. First group label 1 comprises 5 successful requests. I think just speaking about this. We could confirm that they were successful by checking the respective responses. Furthermore, we noticed that each took 3 seconds and indicated by the duration. Second group label 2 shows 16 denied requests. The duration was around 4 milliseconds. It is interesting to check the relative start time as well. The screenshot below shows the whole TCP connection for a request. We can confirm that the post request was sent in a single packet. We can actually open up, it says, the filter says TCP stream EQ18, TCP.stream. So we can definitely start up Wireshark just to check these out. TCP.stream EQ18. Right? So I'll just keep that on and we can definitely analyze. This is a tool that I'm still learning about. But I definitely want to be analyzing whatever I can. And we open the browser again. So okay, let's try sending let's try sending group and sequence over a single connection. So we have our tabs here. It's essentially the same tab duplicated 20 times, 21 times. So here in the send, instead of pressing send, we open the options and we send group in sequence, right? Or yeah, send group in sequence using the single connection. So if we press this button, let's see what takes place. Successful. Successful, successful, successful. Okay, things are still being sent. If you go to Wireshark, should have started already. Something's going on here. But yeah, I'll have to restart. Maybe I'll stop. Continue without saving. Okay, maybe something's going on here. Maybe I chose the wrong adapter. But okay, let's continue analyzing the tabs. Okay. So after tab 5, 1, 2, well, there should be a 2 here, but okay. 1, the 2 was the other one that we got rid of. 1, 3, 4, 5, 6. 6, after tab 6, we have the decline message, right? Excuse me. Of the insufficient balance. So if we remember, we had 4, 1, 2, 3, 4, right? So there are 4 tabs. That's the math that we should do. We had $4 and we lost $4. Essentially now we should have 0.52. I haven't refreshed this. So if we go back, we have 0.52. Because we lost $1, $2, $3, $4 to sending it to the other account. It didn't continue because we don't have enough balance. So then these are invalid requests, right? Okay, so we go to the next one. Send group in sequence over a single connection. Okay, no, send groups in sequence over separate connections. One thing I was doing is that I was refreshing, I was restarting the machine, but maybe I don't need to do that. Maybe the only thing I need to do is to log out and log in to the other account, which is this one. Pass 1, 2, 3, 4. This one has 13, right? So we can close this tab right here. We go to proxy. I usually go here and just clear my history, just so we can work with a clean slate. We go to send group in sequence over separate connections. Again, it's the same thing. Should produce the same type of request. So we go back, we take the other number, we copy that, paste it here, and let's try, since we have 13, let's try 1. Just keep on trying 1, or 1.5 even. Try 1.5. It is successful. We have the post request here, 1.5, the number, confirmed number. So we send it to repeater. We go to repeater. It's the same process that I was doing for the first one. This is a valid request, right? And if we go back, or we don't even need to go back, we have 12.39. Even if we refresh, we have 12.39. If I send this request, something that maybe we should be aware of is if I send this request right now, like so, and I get a response, of course it's a transaction successful because it's within limits. But then if I refresh, the balance is going down. So that's something we should be aware of. So we create a new tab group, transfer. Let's be a little more descriptive. Transfer 1, user 2. Create. Can edit group, transfer 1, user 1. Transfer 1, user 1, transfer 1, user 2, right? So we duplicate this tab 20 times. And essentially, it's the same tab, same request, duplicated 20 times. Okay, great. So now we want to experiment with the second send option, send group in sequence over separate connections instead of single connection, right? Separate connection. I'm still haven't figured out what's happening here. No. Without saving. Let's start it again. Am I choosing the right interface? Seems like so, right? Yeah, seems like so. Okay. TCP stream. Okay, I'll just leave that there. Okay. So we have the second one that we want to experiment with. So we try it. It's sending. So this is where we want to count how many requests were successful. 1, 2, 3, 4, 5, 6. Okay, we're still sending. 7. Yeah, so 7 requests were successful. From 8 onwards, insufficient balance all over up until the last one, which is insufficient balance, right? We minimize that as the name suggests. Yeah, we already read this. The screenshot below shows the whole TCP connection for a request. We can confirm that the post request was sent in a single packet. Should be here, but anyways. Send requests group in parallel. This should be here. I actually tested it the last time. But yeah, maybe I'm doing something wrong. Maybe I'm choosing but yeah, it's probably somewhere over here. Yeah, these are the requests. This is me. So yeah, these are the requests. Again, I'm still learning how to read all of this. It's still pretty new. I'm gonna be honest. A little confession there. So let's go back to we want to try this third one. Send request group in parallel. This third one here. Last byte sync. Choosing to send the group's request in parallel will trigger the repeater to send all the requests in the group at once. In this case, we notice the following, as shown in the screenshot below. In the relative start column, we notice that all 21 packets were sent within a window of 0.5 milliseconds. all 21 requests were successful. They resulted in a successful credit transfer. Each request took around 3.2 seconds to complete. So by paying close attention to the screenshot above, we noticed that each request led to 12 packets. However, in the previous attempt sent in sequence, we see that each request required only 10 packets. Why did this happen? According to the sending group HTTP request documentation, there's a doc for this. When sending in parallel, repeater implements different techniques to synchronize the request's arrival at the target, i.e. when they arrive within a short time frame, right? The synchronization technique depends on the HTTP protocol used. HTTP 2 over, the repeater tries to, or 2 plus, the repeater tries to send the whole group in a single packet. In other words, a single TCP packet would carry multiple requests. In the case of HTTP 1, the repeater resorts to last byte synchronization. We're working with HTTP 1, if I'm not mistaken. Yeah, HTTP 1.1. This trick, the repeater resorts to last byte synchronization. This trick is achieved by withholding the last byte from each request. Only once all packets are sent without the last bytes are the last bytes of all the requests sent. The screenshot below shows our post request sent over. So yeah, that's what we want to try. So let's try this third one. We go back here, we refresh this, so we shouldn't be seeing 10. This is our current balance. So we close this tab, right? We go back to the proxy. I'm just showing you my my perspective and my method. There's like a bunch of ways to do this. I just found it easier to be clearing my history whenever I'm kind of in another process, right, or in another user. In this case, I log out, I go back here. So now we're back to, sorry, it took a slight detour because I think I made a mistake. But then we log into the other user, the one that has all the money in this case. Pass 1 2 3 4. Now, so we're looking at $14 here, and let's clear the history again. We pay and recharge. We grab the other user, which is user 2, and then we load it in, and then we can say 1. Yeah, we can say 1. Say 1. We transfer. It's raining where I am. I'm not sure you can hear, but yeah, it's rain. So we're searching for the post request. Transaction successful, and then we send it to the repeater again. Same process. New type group. This is transfer. This is transfer 2. Transfer 2 from user 1. We're in user 1. Let's keep it purple just to keep consistency, right? 44. Now the purple tabs are users 1. We duplicate it 20 times, right? Let's refresh this. Let's go back to our dashboard. So we have 13.2. We had 14.02. So now we want to try the third one, right? I want to try the third one. we don't want to hit send. We want to select the send group in parallel, last byte sync. This the last byte from each request. Okay, we send it. And then we see that all the tabs are successful. Even if I jump up to this one, everything is successful. And we transferred 1. So 1 times 20 is 20, I'm guessing. I hope I'm so good at multiplying. 1 times 20, 20, but then we all we had was 13. If we refresh the page, we have minus 7.98. So this is a race condition vulnerability, right? Every tab, all the requests are sent. If we go back, you need to get either of the accounts to get more than 100 of credit to get the flag. So what is the flag that you obtain? So we managed to send. Okay, let's maybe log out and then go check the other account. Check the other account. Pass 1, 2, 3, 4. That's user 1. Let's check user 2. One, two, three, 4. Interesting. What's going on here? Okay. So we have a current balance of 22. So we must get either one of them to have 100 to get the flag. So we're gonna close this tab here, and we're gonna pay and recharge. Again, clear our history here. What user are we in actually? Let's figure that out. We're in user 2, so we want to get user 1 to have over 100. Is that possible? Let's see. It's possible. User 1. Let's say 1 for now. We say 1 to get a valid request, and then once we have the request here, 1, we send it to repeater. We can modify it here, right? We know this 1 works, so maybe we can say, let's say 10, and let's do the math, right? If I'll just pull up my calculator on my phone here, because then we need to do the math of how many tabs we'll need to duplicate, right? So okay, transfer 3. User, what user is this? I think it's user 1, if I'm not mistaken. Maybe I am mistaken. But okay, let's put it yellow just to no, it's user 2. Anyways, pull out our calculator. If we say amount 10 times, because we have a limit of duplicates here, duplicate tab. If we say 100, yeah, okay, but 101 does not work because the duplicate button goes gray. So 10 multiplied by 100 is 1000. We don't need that much, but we could go there. Let's say 10 multiplied by 80, or 10 multiplied by 50 even. Okay, let's do 50. So 10 multiplied by 50 duplicates. And then we use the last byte sync, the last one, which worked and which went through. So we send the group in parallel. So we check the tabs. Okay, I'm just gonna skip over some. Okay, everything went through. That means if we calculate well, and if we exploited the race condition here, and we managed to obtain the other accounts, managed to send the more than $100 to the other accounts, right? Now we have to just log into the other accounts. We're in user 1. We're in user 2. We're gonna have to log into user 1, log out. And we get the flag right here. Now we have $500, right? Just 10 times 50 was 500. We come here, we load in the flag. We can even check the other user, which is user 2. Pass 1, 2, 3, 4. And that's how much they have as balance. So continuing with task 6. Sorry about any noise, my city is waking up. So detection and mitigation. Detecting race conditions from the business owner's perspective can be challenging. If a few users redeem the same gift card multiple times, it will most likely go unnoticed unless the logs are actively checked for certain behaviors. Considering that race conditions can be used to exploit even more subtle vulnerabilities, it is clear that we need the help of penetration testers and bug bounty hunters to try to discover such vulnerabilities and report their findings. Penetration testers must understand how the system behaves under normal conditions when enforced controls are enforced. The controls can be use once, vote once, rate once, limit to balance, and limit to 1 every 5 minutes, among others. The next step would be to try to circumvent this limit by exploiting race conditions. Figuring out the different systems' states can help us make educated guesses about time windows where a race condition can be exploited. Tools such as Burp Suite Repeater can be a great starting point. So I think it's really just a matter of using the app, just getting to know it, figuring out like what it does, what it doesn't do, valid, invalid, just kind of like we're checking over here, right? We're seeing over there. Using the features and etc. So mitigation, we will list a few mitigation techniques. Synchronization mechanisms. Modern programming languages provide synchronization mechanisms like locks. Only one thread can acquire the lock at a time, preventing others from accessing the shared resource until it's released. So this provides more, just a bit more order, a bit more organization. Atomic operations. Atomic operations refer to indivisible execution units, a set of instructions grouped together and executed without interruptions. This approach guarantees that an operation can finish without being interrupted by another thread. Database transactions. Transactions group multiple database operations into one unit. Consequently, all operations within the transaction either succeed as a group or fail as a group. This approach ensures data consistency and prevents race conditions from multiple processes modifying the database concurrently. So this was task 6, detection and mitigation. We move on to task 7, which is our challenge. So this room introduced race conditions in various situations leading to such vulnerabilities. System complexity and geographical spread can lead to diverse unforeseen situations, including vulnerabilities related to race conditions. To discover and exploit such conditions, it is vital that we first observe how the system behaves under normal conditions and try to find out how it behaves when we try to exploit the timing. With the currently available tools, we have plenty of techniques to try. All right. So the challenge is to attempt discovering and exploiting a race condition without guidance, right? So we click on the Start Machine button on the right to start the attached VM, start the attack box. I'm still using my own VM. You can use either the attack box or your own VM if you haven't done that already, and browse to this URL. So so we start the machine, we wait about a minute. While it's loading, we can take a look at the credentials. These are the credentials for the 3 users. Raser. I hope I'm reading the names right. Zavodny and Warungi. Raser Kond, Zavodny Stav, Warungi. Whoa, I cannot read this name. Yzigu. So this web application belongs to a bank and allows clients to transfer online money. You need to get one of the accounts to amass more than $1,000. What flag did you obtain after getting an account's balance over $1,000? Okay. So we have the IP address. Open Burp Suite again, just like as a refresher, clean slate. So we have the IP address over here. We load it in. Okay, it's a login form. This, we just make sure this is capturing. All of this is capturing. Great. I said cons of Rodney stuff. Okay, cool. So you can copy this username of what I said. The password is Blue Apple. So the set has $100. We can choose to either transfer to Zavodny or Warunki, or log out. This is the dashboard. It's kind of a refresher. This adds a hash at the end. Okay, let's log out. Let's log into another account. We'll say Zavodny. White Horse. Okay, great. They also have $100. I'm assuming Warunki also has $100, right? So let's just check. Okay, password is green orange. Okay, $100. Okay, great. I think now let's maybe conduct a transfer to Racer. So we have two fields here. 1, 2. We send, and Racer gets. If you have 100, let's send 10. There's a fee, and then Racer gets. Okay. So we have 3 fields. One, it's different than the other one. We didn't really see what the receiver gets, like an estimate or calculated, right? Okay. We'll say continue. It's gonna be successful because it's within accounts limits. Now we have 90. Now let's search for that post request over here. It must be this last one. Yeah, it should be this last one. We sent, so we sent 10. The fee was 0.50 and Racer got 9.50. It says 200. Okay, result true. Okay, so we can send this to the repeater. This is the inspector. We're gonna close it for now. We can do something weird or invalid and see where it gets us. Interesting. If we go back, do we have less than 90? No, we don't. Yeah, because we're supposed to go back and then is this in Warunki's account? That's kind of what I'm asking myself now. Yeah, it makes sense. It makes sense for it to be in Warunki's account. Okay, so we go back to the dashboard. It's 90. Go to Racer. Okay, so this screen usually pops up, and I usually just go to the history and I clear it, since I'm assuming we're going in between accounts so much. Yeah, I think something is happening with my burp. I think it's really on my end. I'm not sure if it happens to you. But once I clear the history and I refresh it, everything's kind of like cool. Okay, to further clear it again. Refresh. Okay. So we go to Racer. Yeah. I'm still getting to know what this is actually. Maybe if I try to log out. Maybe it's something in the request, so I'm just not sure. But okay, let's try to figure it out. Refresh, login. Okay. So let's go back to Warunki, right? Go back to Warunki. Warunki is green, orange. Okay, so we're down to 80. We're down to 80 because of that request that we made over here. Remember, we made a request. This was 10. Now it's 11. It's 80 point what? Interesting. I thought maybe the 1 would matter, but okay. Maybe it doesn't matter that much. Okay. So let's think of this. Let's think of this web application and how we are going to get one of the accounts to amass more than 1,000. We just need to do like some maths between the value that we have. I think the way I'm thinking about it is doing the math between the value that we have and the number of tabs, so that equals the number of requests sent in that time window. Since this race condition of vulnerability within this realm, the timing is key and the time window is key. So I'm gonna I'm gonna pop out my calculator and see how many, if I send $10, so 10 multiplied by, or maybe if I send 100, right? What if I send $100 times 100? No, 100 times 100 is $10,000. So let's say 100 times 20, that's $2,000, right? So for 100 to be a valid request, the account needs to have 100. So let's try to zero out Warunki so we can send Raser all of our money. Okay, so let's try to do that. Maybe not with the repeater, maybe directly from here. Since there's a fee, maybe we could do 70. Yeah, exactly. Let's see if this goes. Okay, successful. Back to dashboard, we have 10. Yeah, okay. 10 is okay. Okay, go back to clear history again. Okay, now we log in as Zavodny because we want to zero Zavodny as well. We don't really need to zero them, but we just want to make sure that we're acting we're kind of requesting within valid territory, right? So Zavodny, we can send 90 to the set. Or what does 95 do? Let's see if it goes. Transaction successful. So Zavodny has 5. Clear history. So now we log on to what I said. Blue Apple. So now the set has nearly 300, right? 275. We can say we want to send to Zavodny, right? If I remember, Zavodny has 5. but Warunki has 10. So let's try to send to Warunki. Let's try to send to Warunki. If we want to send, we have 275 on the status account, right? And if we want to send 100, we don't, the thing is, we don't send 100 yet, because if we conduct this, then we lose 100. We want to save as much as we can so we can have enough headroom over here on Burp Suite's repeater. Since the requests need to be valid, and I think from what I tested, the more headroom you have, the more chances of succeeding you may have. So let's try to send only one to Warunki, but we load in 100 and we take in, we open our okay, this was an old note that I had. Let's create a new one on SQLite payloads. I want to open mousepad. Oh, this is mousepad, actually. Yes, save. Okay. So we load in 100 and we want to take notes of these values right here. So we open our mousepad and then we just type this. Since there are 3 fields, we go back to the repeater, there's 3 fields: the calculated fee, the receiver amount, the fund being transferred, which is 11 or 10, calculated fee, which is 0.50, and the receiver amount. So there are 3 fields we must take note of. If it's 100 that we want to transfer, or we can even transfer 105 or 6, because 106 will still be within range, within valid range. We won't exceed the accounts. We won't exceed the accounts limits, right? So we want to take note of this. I just increase it to 106 just so you can go beyond the fee, just so Warunki has 100, receives 100, right? So we send 106. We do 106, 5.30, and then Warunki gets 100.70. Great. Oh, no. I won't even close this. I'll just minimize it. So we can let go of this. We go back to the proxy and we transfer 1. We're transferring 1 to Warunki, meaning this is the post request of the transfer. 1, okay. So we send this to the repeater, and then in repeater, that's when we take out our mousepad, 106, 5.30, 106, 5.30. Now we're modifying our request, right? Warunki gets 170. And we don't hit send yet. So far, we know we have just a $1 less than we did, right? It was 275, now it's 274.75. So we create a new tab. We can say transfer 1 to Warunki. And we add 2, tab 2. Choose a blue color. And then we duplicate. Now the duplicating the number needs to add up, right? So 100 times 20 is what we used to say. We could bring it up a notch to 100 times maybe like 50. I mean, it's a lot, but we'll see that some errors will or might occur when we try to do this, some unexpected behavior. But okay, let's duplicate this and let's do 50. That will give Warunki 5,000 actually, right? So because he gets $100 times 50 times. Right, these are 50 tabs. So, okay, let's choose the one that worked. Send group in parallel. That was the third one. And we're gonna hit send. Just gonna see what happens. Just check our values again. This is what we want to send. This is our fee, and this is what Warunki gets, right? This was in the transfer page. We haven't sent anything yet. So we're in the set. If we're taking out 100, it's still within the range of 274. So let's try it and see what happens. So when we have a result of true, that means it went through, right? So now we just have to check. You see, we have a 500 internal server error. The server encountered an internal error and wasn't able to complete your request. Either the server is overloaded or there is an error in the application. So I think this was the unexpected behavior that I was mentioning from the server side, and some requests are dropped. So that's another form of headroom that you want to kind of be aware of. If we had done just 20, maybe half of the 20 would be, in the 500 internal server error side. So maybe now just half of the 50, or half, I don't know, maybe it's not even close to half, or just a little bit more than half. But all we need to do now is just to count the hundreds, because how many tabs we have is how many hundreds we've managed to transfer to Warunki. All right, sorry about the noise again. So we count the tabs: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So now we know that Warunki has over $1,000 because, well, 100 times 11, that's $1,100, right? It's this value right here. This is what Warunki received. This is what we sent. This is the fee, but this is what Warunki received. And if we log out of Racers, and if we go to Warunki, Warunki is green-orange. Warunki has 1,219 USD, and this is the flag. So that was the race conditions lab. Yeah, I think it was a very interesting lab, and it's a very interesting vulnerability. And yeah, that was my walkthrough of the race conditions lab. I think it took me some time. I had to read through things again, read slowly, understand each line of what was being explained, and I think it really helped just to like test things, go wrong with things. There are other ways to do this to solve this challenge. I'm just showing you my approach. For example, the first time I did it was a little very different than how I did it in terms of the math, in terms of like the methodology and everything. So yeah, hope you liked the video, and until the next one.